All right, so in the last video we talked about symmetry tests for graphs of polar functions. That's one thing that's oftentimes worth looking at when you're graphing a new function from a polar equation. Another thing that's going to be informative about a graph is the zeros and the maxima of an equation. And what we mean by maxima, we really mean maxima and minima, which are the largest and smallest values of r you can get from an equation. So let me start with zeros. When we say find the zeros of an equation, we specifically mean what are the values of theta that produce a zero for r, if any exist. And in some cases, you don't get that at all. So what we do is we set r equal to 0. 0 equals 2 sine of theta. And we basically just solve this equation. Okay, sine is equal to 2 times sine of 0, sorry, 2 times sine of theta will equal 0 if sine of theta is equal to 0. And that happens at every multiple of pi. Theta equals pi k. Now, oftentimes, it's not really the values of theta that are the most important thing to know when finding the zeros, but rather that this equation has a solution at all. So what this means is that if we were plotting points, and we're going to look at that in a moment, into this equation, by plotting points, what we do is we plug in different values of theta to produce corresponding values of r. That gives us a bunch of points in polar coordinates, points of the form r theta that we could plot in the plane. The fact that this happens at all means that there is a point on the graph of this function where r is equal to 0. And if you remember from 10.3, whenever r is equal to 0, it doesn't matter what theta is. That's always going to represent a point at the pole. So the fact that a solution to this exists means that the graph of this equation will contain the pole, or the pole will be one of the points on this graph. That's what finding the zeros tells us. Now, as far as maxima and minima, I'm going to say max, min. What we're doing is we're looking for the largest and smallest possible values that we can get for r. And this is going to be determined by considering the range of the sine function. We know that the smallest sine of theta can be is, we call the first one a min. The smallest sine of theta can be is -1. So the smallest that r can be is 2 times -1 or -2. I probably shouldn't use that symbol. That looks like a negative. Similarly, the maximum value I can get for r is going to be when sine is equal to +1, because that's as large as sine can be. 2 times 1, which is 2. Okay, so r is minimized at -2, maximized at +2, which means for any point on this graph, the value of r is always going to be something between -2 and +2. That means no point on this graph can be more than 2 units away from the pole. So this gives us more useful information. But let's go a step further and actually graph the function we've been working with in these last two examples, r equals 2 sine of theta. Now this is actually from an example in your book, so we want to plot points to graph this function. What I'm going to do is, or what you would normally do is create a table like this, and we think of theta as your independent variable. This is the variable that we plug values in for. Because theta represents an angle, it's easiest to choose values that are from your unit circle. So you see some values from the unit circle here plugged in. We go from 0 to pi for this example. Now, plugging in these values for theta, we get the corresponding values for r, which you can verify that directly by looking at the work that's done here. Okay, so these create points. And remember, when you write a point in polar coordinates, r actually comes first, followed by theta. So this would be the point 0, 0. This would be the point 1 pi over 6. Here, we approximated this to 1.73. For the purpose of plotting points, you don't want to leave things in radical form, because it's not really all that clear if something is left in radical form, where you would be plotting a specific point. So this you plug into a calculator, get an approximation, so on and so forth. You can see the largest number in this list is 2, and just like in the previous example, we know that would be the case because we said that the maximum value that this function can attain is 2. Okay, so if you were to plot all of these points in polar coordinates, you're going to see them show up here. What we end up with is a circle. And the circle contains the pole, which we on the previous example we said that would be the case. This is because the equation has a 0. It's also symmetric about the line theta equals pi over 2, which we verified in that symmetry test. You can see the symmetry pretty clearly. It doesn't have symmetry about our horizontal axis or the pole. And remember, even though those two symmetry tests failed in the previous video, that's not a guarantee that this wouldn't have that type of symmetry. It just turned out to be the case here. Okay. One other thing worth noticing, this circle has a diameter of 2. You can see 2 right here. That diameter corresponds to the coefficient on this sine function, and that's not a coincidence. That's going to happen in the general case as well. So let's look at the general case. Anytime we're looking at an equation of the form r equals a cosine of theta, or r equals a sine of theta, where a is some non-zero constant, we get a circle, but not just any circle. It's a specific type of circle. The circle will always contain the pole. You see all 4 of these examples, the pole is included on that circle. And the circle is always going to open away from an axis. So here you can see that we're kind of opening away from the vertical axis. The symmetry that we get in this example is symmetry about the polar axis. Same with this one here. Here we get symmetry about the line theta equals pi over 2. But in any time we're dealing with a function or an equation of the form r equals a cosine or r equals a sine of theta, we always get a circle of this type. A tells us what the diameter of that circle will be. The diameter is always the absolute value of A. We need to say absolute value because in some of these cases, A is assumed to be negative. And then in addition to that, the way that we determine which of these 4 cases we're looking at boils down to 2 things. One is the sign of A, and when I say sign, I don't mean like the trigonometry sign. I mean whether it's positive or negative. So whether A is positive or negative, or whether as well as whether this function is a sine or a cosine. Different combinations produce different types of circles. So notice if we have a cosine with a positive coefficient A, it's going to the circle is going to be symmetric about the horizontal axis. In fact, if we have a cosine here at all, that's always going to give us symmetry about the horizontal axis. You can use your symmetry tests to verify that. But we have a circle on the right if A is positive, a circle on the left if A is negative. Similar for sine. If we have a sine here, we're going to have symmetry about the line theta equals pi over 2. So the circle will either be above or below the polar axis. And we know it's above if A is positive, below if A is negative. So knowing these different cases allows you to graph these circles without having to go through all of the work of plotting points like this. In fact, the goal for this section is to avoid this as much as possible. Now, when you're dealing with a brand new graph that you've never graphed before, a new type of equation, this is maybe your only option. You can also do those symmetry tests and look for zeros and maximum and minimum values. But knowing some patterns makes the graphing a lot faster. So let's look at how we can graph this without having to actually plot points. The circle in this case is -4 cosine of theta. So I'm going to draw my axes here. Okay. Now the fact that we have a cosine means that the circle is going to be symmetric about the horizontal axis, the polar axis. So it's either going to be a circle that looks like this one or a circle that looks like this one. But the fact that we have a negative coefficient is what narrows it down to this case, where the circle opens to the left. So I'm going to be sketching a circle that goes to the left. Now the diameter of that circle is going to be the absolute value of this coefficient. So the diameter should be 4. Okay, we know that we also have a point here at the pole. Now, one other thing I want to do, you notice I'm not using a polar grid. I'm not sketching those circles here. And that's because you can actually get away without doing that for this graph. If the diameter of this circle is 4, then half of that gives us our radius, which would be 2. I'm going to put a 2 here and a negative 2 here. Not only that, the circle would be centered, sorry, that should be a negative 4 right there, shouldn't it? The circle will be centered at the point negative 2, 0. So there's going to be a center right here. This allows me to plot a few points that are going to lie on this circle. 1, 2, 3, 4. Now my circle looks a little bit elliptical because I'm doing this freehand. It doesn't look perfect, but that gets you the basic idea. And again, I'm not worrying about being super accurate with all of the points around this circle. These are the 4 that I care about the most, and I didn't need to actually go through and make a big old table like this up here to graph that circle. Okay, so circles are the first types of graphs that we look at in this section, but there's a lot more. So next up, we're going to look at what are called Limasons. The term Limason, I believe it's French. It stands, or it means snail, and that's because for some reason whoever decided to give these graphs this name thought that the graphs resembled the shell of a snail. You can be the judge of that, but that's what we're going to be looking at for probably the next couple of videos. Limasons come in a few different forms that we need to investigate. But you know that you're looking at a Limason if you have a graph of one of these types, or an equation of one of these types. It's always going to look like r equals a plus b sine of theta, or minus, so plus or minus could be here, or r equals a plus or minus b cosine of theta. It's going to be one of those two types. Okay, now the graph of let's look at the first type of Limason. So relationships between A and B determine these different types of Limasons. Your book gives you a description that might be a little bit confusing, so I'm gonna kind of explain this in what I believe to be an easier way to wrap your mind around. This first type of Limason is what's called a cardioid, and we always get cardioids when you have an equation of this form and A is equal to B. So A and B would be equal. Okay. Now, we call these cardioids because they kind of resemble hearts. You can see that this makes somewhat of a heart shape. It's like a very round heart. We could go through and plot points if we wanted to, but I'm gonna take a look at this thing and think of it in terms of its zeros and its maximum and minimum values. Okay, so let's start with zeros. I'm going to do this example, then we'll come back and look at the different cases up here. So if I want to graph a cardioid and I'm trying to find where its zeros are, I'd be plugging 0 in for r. 0 equals 2 minus 2 sine of theta. Now if I were to subtract a 2 from both sides and then divide both sides by negative 2, I get 1 equals sine of theta. This has a solution. I'm going to keep my solutions within one revolution of the unit circle. So the solutions I get for this are theta equals pi over 2 and 3 pi over 2. Okay? The fact that solutions exist, though, mean that the graph of this equation will contain the pole. And that's the reason why all of these cardioids have this little point, this little kind of... it kind of comes into a point here at the pole for each one of these. The pole is on the graph, and this is the reason why. Now, how about maximum and minimum values? Well, in this case, how do we maximize this function? Okay, now in the previous case, the previous example, we said, well, sine is maximized when it's equal to 1. But if I plugged a 1 in for sine of theta, then I would get 2 minus 2, which is 0. That's a small value. In fact, that's what we're getting up here. So that's actually a minimum. The minimum occurs when sine is equal to positive 1. 2 minus 2 times 1, which is 0. The maximum occurs when sine is equal to negative 1. And the reason for that is because we get 2 minus 2 times negative 1. In this case, I have a negative times a negative, which gives me a positive. Positive 4, in fact. Okay? Now, from these graphs of these cardioids, you can see that the maximum occurs at this point here, or here, here, or here, depending on which case you're looking at, this farthest point. So if I were to graph this cardioid, first of all, notice that the orientation of these things is similar to with circles. I'm dealing with a sine function here, sine of theta. And the way that I can tell which of these three possibilities I'm looking at is going to be determined based on B, whether B has a plus or a minus in front of it. Remember, B is the coefficient on my sine here. If you read this carefully, you'll notice that in the graph of a cardioid, and this is true for all Limasons actually, we always require A to be positive. So if you notice, I have a positive value for A right here. So really, it's the sign of B that's going to make this determination. Sine means that we're going to have symmetry about the vertical axis. The fact that this is a minus means that the cardioid will open down instead of up. So what I'm going to get is a heart shape, that cardioid shape, that does something like this. Okay? Now, I can't just leave it like that, because I'm not labeling anything. I need to know the labels for my axes. But I do know that my maximum value, which is 4, clearly from this graph is going to show up here. That's the point that's furthest from the pole. So that should be a 4. I want to make sure and label that. Okay. These 2 points, there appears to be symmetry here. In fact, we know there's symmetry here. So if I know this point, then I can take the opposite of that number and find this point. How do we get these points, though? Well, I'm looking at this and I'm noticing that the point here, if I were to find it in polar coordinates, the angle that it creates is an angle of 0. So I can find that angle just by plugging 0 in for theta. Sine of 0 is 0. So this becomes 2 minus 0, or 2. So there's a 2 right there. That would make this negative 2. Okay, now notice, where did that 2 come from? Well, when I plugged the angle 0 into theta, this entire term went away. So this value right here actually was just whatever A was equal to. And this gives us kind of a technique for graphing any cardioid. Boils down to a couple of things. One, you have to determine the orientation of your cardioid. Is it opening right, left, up, or down? Then you have to determine some labels. We know that no matter what, cardioids always contain the pole, but you're going to need this maximum value and then these 2 values that are on opposite sides of whatever axis our symmetry is occurring about. To get this value, either the 2 or the negative 2, it's just equal to A, plus or minus A, whatever that happens to be, positive 2 and negative 2. And that's true for any cardioid. This value right here is going to come from adding A to B. And again, when we consider B, we're not considering this minus here as making this negative. So by A plus B, what I mean is 2 plus 2 in this case, which is 4. Because these 2 values are always equal to each other in a cardioid, that's the same thing as doubling this number. So in a different case, if I had graphed a cardioid and say that both of these values were 10, I would know immediately that this value here is 20. Okay? We're out of time for this video. We'll look at some more Limasons in the next one.